In this section, we're going to look at finding the volumes of solids that are obtained by revolving regions bounded by curves about some particular axis, either the x-axis, the y-axis, or a line parallel to one of those two. So I have here drawn, shaded in yellow, a region that we can revolve about the x-axis. Now the resulting solid, I won't say my best, but I've done an attempt over here at the bottom to draw what it would look like if you take this yellow region and revolve it about the x-axis. You could imagine just this flat surface moving in a circular fashion around the x-axis there. And so the question is, assuming that this is a solid figure and not some little tube, what is the volume of the solid that is generated by doing that revolution? We're going to develop two different methods. In this particular video, we're using the disk and washer method, so let's approach with that. When we first learned about integration, we chopped up our interval from A to B into subintervals. And so I'm going to do that. We're just going to take some subinterval from here to here. What we did was we created a rectangle on top of that. So I'm going to draw a rectangle on top of that. There is my rectangle. Now I'm going to, instead of imagining revolving the entire region about the x-axis, I'm only going to revolve this rectangle. Now when I do it, we'll end up with a mirror image of that rectangle on the other side of the x-axis. Best mirror image we can do here. And then we'll basically create for ourselves this little disk. Looks like so. Okay, so this disk, let's do the borders of the disk in blue so it's clear here. This disk is going to help us determine what the volume of that cylinder or of that region is going to be. Those straight lines there are really just reference points. Now think about the disk. If we lay it on its side, it's going to look something like this. And those of you who have favorite geometric figures, you'll recognize that this is a cylinder. Okay, because it's a cylinder, its volume, the volume of a cylinder is the area of the base. Well, to get the area of the base, we need to know the radius. That would be pi r squared. And then we'll multiply that by h, which is the height of the disk. In our case, this is a pretty thin h, but that's okay. So that's the general formula that we're going to use to create the volume of this particular disk. And then what we would do is we would add them all up. Now, adding them all up and letting the width of those disks go to 0, or letting the number of disks go to infinity, that's the process of integration. So what we need to do is we can find the area or the volume of this little disk and then sort of do the integral of that. Now I'm going to kind of cheat. This really should be thought of as delta x. The width across here we should think of as delta x. But instead of doing delta x, I'm just going to think of that as being dx. If I want to plot a point here, let's just plot the point where it intersects the x-axis, or intersects the curve. We'll do that in red here. That would be the point x comma y. Now our function is going to be some function of x. As x changes, y will change. So x comma y is the same as x comma f of x. Now this is important in order to come up with the formula for the volume of the disk. The volume of the disk then will help us calculate the volume of the solid that we generate. We're going to need the radius. Well, the radius in our particular picture is going to be this distance here. Think about which direction we're moving. We're moving up and down. If you move up and down, if you take a point and move it up and down, you're changing its y value. So the radius in this case is the y value of this point, which is f of x. Now this will vary from problem to problem, but in this particular case, my radius is going to be f of x. The height of the cylinder is moving this way, and notice we're moving horizontally, left and right. So if we're moving horizontally, that is a change in x, so my height is just going to be dx. And as I said, we're kind of cheating. When we put this all together, the volume is pi times my radius squared times h, which is pi times f of x. F of x was our radius. We're going to square that, multiplied by dx. Again, dx is kind of wishy-washy, but it's okay to do it that way. Since we'll be doing this from A to B, the volume we'll do over here is going to be the integral from A to B, pi r squared h. Pi times f of x squared, h is dx. So that's the formula that's kind of the basis for what we'll do. Now, it will change from problem to problem, so we need to think through each step, but that's how we'll proceed with this. And often, we like to put the pi out front, but I didn't do that in this particular case. So here are some problem-solving strategies. First of all, absolutely positively graph the function that you're trying to revolve about the x-axis or whichever axis it is. Draw all the little pieces that we have there as well. The radius, the thickness, and so forth. You might want to draw several different rectangles that represent the Riemann sums. That just helps you determine if you have to make some changes along the way. Is one function on top early and another function on top later? Sometimes we'll be revolving about the y-axis. So in those cases, the disks, instead of being up and down, will be sort of already laying on their side like so. The y-axis kind of running through the middle of that. Find a formula for the radius. And now I say disks and washers. Well, this is a disk. Let me talk about disks and washers for a minute. A disk is something like this, where you have a full solid cylinder. A washer, if you think about washers, not that clean your clothes, but that help you make things, washers are these things with holes in the middle. And so sometimes we'll have holes in the middle of our figure that we need to account for and take away. We'll talk about that when we get to it. Again, is there a hole in the resulting solid? Holes occur when there is space between the region that we're revolving about the axis and the axis itself. If so, we need to use the washer method. We'll get to that in a little bit. You have to square the function before you subtract the lower from the upper. What? Before we... Okay, so if we have a washer method situation, we're basically going to be taking two volumes, subtracting one from the other. You want to square the radiuses before you do that subtraction. It helps to label x and y pairs. When you measure distances between things that are vertical, we're doing some sort of change in y. When we do things that are horizontal, we're moving in the x direction, so you would do some sort of change in x. And the radius is always the distance from a point on the curve to the axis of revolution. Let's look at our first example. We want the volume of a solid generated by revolving the region bounded by y equals 2 plus 1/2 x, a nice linear function, the coordinate axes, and the line x equals 3. We're going to revolve that about the x-axis. Okay, so let's draw these things. Okay, so here are our axes, and I've thrown some points on there. Our function is 2 plus 1/2 x, so the y-intercept is 2, and my slope is 1/2. That means I'm going to go up 1 and over 2. So up 1 and over 2 will land me about here. Up 1 and over 2 would land me about there. And then we can draw the graph, and when we draw it, we end up with something like this. I kind of missed that other point there, but that's okay. Let's fix that point there. We'll cheat. So there's our other point. So we want to revolve the region bounded by the curve. So let me draw my boundaries. There is the line. Okay, now I'm going to stop because one of my other boundaries is the line x equals 3. So that's this line there. And then it says the coordinate axes. So the y-axis and the x-axis will be my other boundaries, and we get this little trapezoid shape here. So we want to revolve that region about the x-axis. Let's shade that in. So let's draw a typical rectangle here. A typical rectangle might be over here. It doesn't really matter where we do it, although we should really think about what happens as we move it along. So there is my typical rectangle. If I move it left and right, notice the bottom of the rectangle is always on the x-axis, which means there's no space between the region that we have and the axis we're revolving it about. That's important. The top of the rectangle would always be along that particular line. Okay, so let's draw the rectangle, and we're going to reflect it about the x-axis here. And we'll draw our cylinder. So here is our disk. Okay. So we need to find the volume of that disk. Volume of a disk, remember, is pi times the radius squared times h. Okay, h is the thickness. Now, our thickness is moving this away, left and right. So it's either going to be dx or dy. Because I'm moving left and right, we're going to call that guy dx. My radius is the radius of this disk, which is going up and down. If we're going up and down, then my y value is changing. So I need to know what my radius is, the y value, but I was told way up here that y is equal to 2 plus 1/2 x. My volume then is going to be pi times the quantity 2 plus 1/2 x squared times h, which is dx. That will be our integrand, and again, we like to pull the pi out front. Our boundaries, we start at x equals 0, and we stop at x equals 3. So we will integrate from 0 to 3. The volume will be pi times the integral from 0 to 3, 2 plus 1/2 x quantity squared dx. There are a couple of ways you can do this. You can do this by substitution, or you can expand it out. We'll just go ahead and expand it out. It's going to be pi times the integral from 0 to 3. It'll be 4 plus 2x plus 1/4 x squared dx. And then we integrate. Pi times 4x plus x squared. Ooh, this is going to be an ugly fraction. 1/12 x cubed evaluated from 0 to 3. Fortunately, when we evaluate it at 0, we will get 0. Pi times, so 4 times 3 plus 3 squared plus 1/12 of 3 cubed, which, after simplifying, is 93 pi over 4. For our next example, we have a solid that's generated by revolving the region in the first quadrant, bounded by y equals e to the x squared, x equals 0, that would be the x-axis, and y equals e. We're going to revolve this about the y-axis, and we need to find the volume of the solid. Here is our graph. You're welcome to use a graphing calculator. Now we want to graph y equals e. I haven't added that to the list here. E is about 2.718, so it's going to be up here. Now let's find the boundaries once again. It says we're only going to do the region in the first quadrant. So that's the right half of this graph. Y equals x e to the x squared, so we want this part of the graph. X equals 0, that's the x-axis, and y equals e is going to be up here. When we look at the region bounded, it's this region inside here. We're going to revolve this about the y-axis. Now the y-axis is a little bit different, but we can draw it just like we did before. So pick a typical rectangle. There's a nice little rectangle. And we're going to revolve this about the y-axis. When I do it, it's kind of nice. This particular graph already has the mirror image built in. So it's going to look something like that. Let's shade the region that we're graphing here. So that's going to be the side of our disk. And now let's make it nice and solid. Let's draw the rest of the disk like so. Okay. And so you want to keep in mind that volume equals pi r squared h business. Now, h, once again, is how thick our particular disk is. Our thickness, though, is moving up and down this time. Since it's moving up and down, that's going to be a change in y. When we move up and down, it's changes in y. Our radius is going back and forth. Okay, so this is our radius up here. Well, if I'm moving back and forth, left and right, that's an x value. Ooh, okay, well, I don't have what x is equal to. So we're going to have to do a little bit of algebra for this particular problem. Now, here's another reason I know I have to do some algebra. Because I have dy here, because my thickness is dy, that means I'm going to integrate with respect to y. Now, let's look at how our function is given to us. Our function is given to us where y is a function of x. Because y is a function of x, and I need to integrate with respect to y, that's not going to work for us. So we're going to go back to the drawing board, take my equation here, and solve it for x. Well, I've got y equals e to some power. We're going to use logarithms. If you use logarithms, you'll get the natural log of y is equal to, that would be the exponent, x squared, which means I can take the square root. X will be equal to the square root of the natural log of y. I should be concerned, do I want the positive root or the negative root? Because x is in the first quadrant, because our region is in the first quadrant, x will be positive, so it's okay to leave it as the positive square root. So my radius now, if I go back over here, my radius is going to be the square root of the natural log of x, which makes me nervous, but I remember that I'm going to square it in a little bit here. So it's time to put all the pieces together. The volume is pi, integral here, times my radius squared, the square root of the natural log of x, quantity squared, times h, pi r squared h. H is dy. And I've lied to you. This isn't the natural log of x. That should say the natural log of y. Okay, now one thing that's missing from this are my limits of integration. Be very careful. You've got dy back here. My integral needs to go in terms of y values. So let's look at the y values. The y values start down here. Well, that's at y equals 1. And they end up here. That's at y equals e. I'm going to vary between y equals 1 and y equals e. So I'm going to go from 1 to e. Let's simplify. We get pi times the integral from 1 to e of the natural log of y dy. When I see a natural log in an integral, I know that I could try substitution, but 1 over y would have to be present, and it's not. When that's not the case, then we use integration by parts. We choose one thing for u, one thing for dv. U we differentiate, dv we integrate. If I knew how to integrate the natural log of y, I wouldn't be in this situation in the first place. So u is going to be the natural log of y. Du will be 1 over y dy. dv, on the other hand, is everything else, which in our case is dy. So when I take the antiderivative, v is going to be equal to y. So it's uv minus the integral of v du. Don't forget, you've got the pi. We're going to do that difference, u times v, so we need a parenthesis. y times the natural log of y evaluated from 1 to e minus the integral. We're going to multiply v times du, y times 1 over y dy, evaluated from 1 to e. Let's do some calculations. Pi times, okay, we'll do the first piece. When y is equal to e, we get e times the natural log of e. When y is equal to 1 minus 1 times the natural log of 1. And whenever I do that, I'm going to put a big 0 because the natural log of 1 is 0. And then we have to do minus. Now we've got to fix this integral. We have to multiply the y by the 1 minus y before we integrate. That's the integral from 1 to e of simply dy. E times the natural log of e. The natural log of e equals 1. Pi times e times 1. And then we take the antiderivative of dy, which is just y, evaluated from 1 to e. Be careful as you evaluate this. Okay, be careful as you evaluate this. This will be equal to pi times e minus, now we have to do a parenthesis. When y is equal to e, we get e. When y is equal to 1, we get 1. And when we simplify, we end up with simply pi, because the e's one will subtract from the other. Our next example involves a trigonometric function. We're going to take the solid generated by revolving the region bounded by y equals the sine of x equals 0, and x equals pi. We're going to revolve that about the x-axis. We also want one of our boundaries to be the x-axis. Here is the graph of our function. Let's shade the region we're bounding by, or the region bounded by these things. There is the region that we're going to revolve about the x-axis. Okay, so we do the same thing we've been doing. Notice that once again, our region is bounded by the x-axis. Our axis of revolution is also the x-axis. There is no space between them. We'll see soon an example where there is, and we'll see what has to happen here. So here's one rectangle. This rectangle, its bottom is on the x-axis, the axis of revolution. Its top is on the curve of y equals the sine of x. If I were to move it left and right, we haven't talked about this much, but if I were to move that triangle left and right, the bottom would remain on the x-axis, the top would remain on the sine of x. So those don't change. Here we go again. I need to know what the thickness is. Well, I haven't drawn this whole thing out yet. Let's draw the mirror image of that rectangle. And then let's draw our cylinder. So our cylinder, ooh, I picked a bigger marker there. Our cylinder looks something like this. And so we need the thickness. Well, the thickness this time is moving left to right. So the thickness, because I'm moving left to right, it's going to be dx. And my radius is the radius of this disk, which is moving up and down. The radius is moving up and down, so it is y, which just above that is equal to the sine of x. The volume is pi times my radius squared times h, which in our case is pi times, well, we're going to square the sine, so sine squared of x, h is dx. Because I'm integrating with respect to x, we start at x equals 0. We end at x equals pi. Those are my limits of integration, 0 to pi. Our volume, therefore, is pi times my radius squared. Well, I'm going to do the integral from 0 to pi. My radius is the sine squared of x, or the radius squared is sine squared of x, dx. Okay, this is a tricky integral. You either need to use a trigonometric identity which I'll list here in just a moment, in order to evaluate it. Or you can actually use integration by parts. It's kind of a funny circular type of thing, so I prefer using the half angle identity. So the half angle identity says that the sine squared of x is equal to 1/2 of 1 minus the cosine of 2x. So I'm going to bring the 1/2 out front, 1/2 times pi. And then we're going to do times the integral from 0 to pi of 1 minus the cosine of 2x dx. We get 1/2 pi. The antiderivative of 1 will be x. The antiderivative of the cosine of 2x is the sine of 2x. But because of the 2 in there, we're going to have to compensate out front by multiplying by 1/2. You could use substitution by letting u equal 2x, but if we can think backwards, that saves us a little bit of time. So I end up with 1/2 pi. X at pi becomes pi minus 1/2 times the sine of 2 times pi. And then let's substitute 0 in. Now, we need to be careful. There's a trig function in here, and sometimes trig functions behave funny. When x is equal to 0, certainly we do get 0, minus 1/2 the sine of 2 times 0, which will be the sine of 0. Now let's evaluate our trig functions. Our trig functions are the sine of 2 pi, which is 0, and the sine of 2 times 0, the sine of 0, which is also 0. So we have lots of zeros all over the place, and we just end up with a final answer of 1/2 pi times the pi that's remaining in here, so 1/2 pi squared. For our next example, we're going to see something where we do have space between the region that that is bounded by the curves and the axis of revolution. Okay, so let's look at this particular function. Here we have a set of axes that we'll use. Radical 4 minus x, I know that if x is equal to 0, we'll have radical 4, which is 2. If x is equal to 4, we'll have 4 minus 4 under the root. That's the square root of 0. And if x is equal to 3, we'll have 4 minus 3. The square root of 4 minus 3 is the square root of 1, which is 1. So this function looks something like this. Y equals 1 minus 1/4 x is a linear function with y-intercept equal to 1 and a slope of 1/4. So we're going to go down 1, or negative 1/4. We're going to go down 1 and over 4 so that we intersect at that point as well. So here is the region that we're going to revolve about the x-axis. You'll see why I'm drawing it in green in just a moment. Okay, if I draw a typical rectangle, let's just draw this one. Okay, there's my rectangle. Notice that there is space between the bottom of that rectangle and the axis of revolution. We're going to revolve it about the x-axis. There is a space between those two objects. Okay, what that means is we're going to treat this like a washer. Okay, so we will draw our cylinder, but it will have a hole in it. Okay, so actually it looks like I'm drawing the hole first. The hole we should think of as being something in red. And we're going to take away that particular volume. Okay, now let's go with the rest of it here. Here's the other side of that rectangle. And now let's draw the rest of the cylinder. We'll do this in blue here. Okay, so here is how we'll create a formula for this particular volume. The overall volume is going to be the volume of the outside disk. That would be the one that extends from the very top of this down. We're going to imagine that we're actually taking in this entire region. And then we're going to take away the volume of the inside disk. The volume of the inside disk is the volume in this particular region down here. In order to do that, we need the radius of the outside disk and the radius of the inside disk. Okay, the radius of the outside disk is this. Okay, I drew it off to the side so we can see it a little bit better, but it traces over there. Now, if you think about what I drew something that's going up and down. So my radius is the y value for where the top of that rectangle intersects. Well, that rectangle intersects the parabola here, which is the square root of 4 minus x. That's going to be my outer radius. My inner radius on the other hand, is going to be the radius of this little hole that we dug out of our cylinder. The inner radius is along the line here, and the line has equation 1 minus 1/4 x. When we set these up, the volume of the outer the volume of the outer cylinder would be pi times my radius squared, my outer radius squared, that is, times the thickness. Now, we haven't discussed the thickness, but the thickness of this rectangle is moving left and right. That's going to be dx. That's the height. So in our case, that's going to be pi. The outer radius, we said, was the square root of 4 minus x quantity squared multiplied by dx. And the volume of the inner radius is going to be pi times the volume of the inner cylinder is pi times the inner radius squared times h, which is pi times the inner radius is 1 minus 1/4 x quantity squared dx. Okay, the biggest challenge in all of these problems is setting up the integral. Now, sometimes the integral can be challenging. We saw earlier where we had to use a trigonometric identity. You might have to use integration by parts like we did in another one. This one's not too bad. So the volume of my solid is the outer volume minus the inner volume. Okay, the outer volume would be pi. Oh, we haven't discussed limits. We have to know our limits. We are integrating with respect to x. Where does this region start? The green region starts at x equals 0. And the green region ends out here when x is equal to 4. So our integral is going to go from 0 to 4. Now our outer one, I'm going to do a little simplification. You can trace it from over here. But our outer one will be pi times 4 minus x squared. Well, the square root of that squared is just 4 minus x dx. And then we do minus pi times the integral from 0 to 4 of the inner one. And the inner one is 1 minus 1/4 x quantity squared dx. Okay, now, typically when we do these problems, we don't set up two separate integrals. I think there is actually an advantage to that because it avoids making a mistake. We are squaring both of our radiuses individually. One common mistake is that students will subtract one radius from the other and square them after that. That's not going to give you the correct answer. So usually we'll do this as pi times the integral from 0 to 4 of a single integral. So it would be 4 minus x minus the 1 minus 1/4 x quantity squared dx. Okay, so it's the outer radius squared minus the inner radius squared. We have to take this integral. The first one is pretty straightforward. We just use ordinary formulas. So we'll end up with pi. The antiderivative of 4 is 4x. The antiderivative of 1 is 1/2, or of x is 1/2 x squared. Now the second one has what we've called before in other videos as a linear argument here. 1 minus 1/4 x is a linear function. So we can treat that kind of like it's just an ordinary x squared. What would the antiderivative be of x squared? It would be 1/3 x cubed. Now I'm going to leave a little space before I write the cube part, but it'd be 1 minus 1/4 x quantity cubed. We're going to evaluate this from 0 to 4. My answer is incorrect, though. It's incorrect because when I use that little idea of, oh, well, this is a linear argument on the inside, we have to compensate for the derivative of the inside because of the chain rule. The derivative of 1 minus 1/4 x is negative 1/4. So we have to multiply by the reciprocal of that on the outside. So we're going to multiply by negative 4 on the outside to compensate for the negative 1/4 x on the inside. Okay? So I'm going to do a little combination here. These two together multiplied will give me 4/3. Not a very pretty fraction. And now we're ready to substitute. I'm going to do this carefully, but let's see what we get. We end up with pi. When x is 4, we'll have 4 times 4, which is 16, minus 1/2 of 4 squared, which is 16, minus, well, it's actually plus 4/3, is it not? Plus 4/3. Let's see here. And then we'll have 1 minus 1/4 times 4 quantity cubed. Now that's the first part of it. Okay. The second part, when we do this, we'll have minus pi times 16. Oops, excuse me, we've already done that part. When x is 0, 4 times 0 is going to give me 0. 1/2 x squared when x is 0 will also give me 0 minus 0. And then this is where we've got to be super careful. This is going to be plus 4/3 of, when x is 0 now, 1 minus 1/4 of 0, 1/4 of 0 is 0, we'll get 1 cubed. Okay, so we end up with, what do we end up with? We end up with 20 pi divided by 3. Our last example is quite a sophisticated example. Okay, so let's take a peek at it. We have, once again, we're going to take a solid. We're going to generate it about, we're going to take that region and we're going to revolve it, this time about the line x equals negative 2. Okay, so this is going to be a little bit more challenging. Our region is the region bounded by y equals 2x and y equals x squared. So let's get to business here. I've started off by drawing my axes and drawing the axis of revolution. Our axis of revolution is x equals negative 2. Now notice that this line is a vertical line. In order to determine how to do this problem, we want to think about what coordinate axis this is parallel to. X equals negative 2 is parallel to the y-axis. So this will be like any other problem that we've done where we revolved it about the y-axis, but we've got a little bit more work to do. So let's graph our functions. Y equals x squared. When x is equal to 1, we get 1. When x is equal to 2, we get 4. When x is equal to 0, we get 0. So this is y equals x squared. I'm not going to draw the other half because I know what's coming. For y equals 2x, when x is equal to 0, we get 0. When x equals 1, we get 2. And when x equals 2, we get 4. So the reason I wanted to not draw too much is because the region is bounded by those two curves, and it's this little almost banana-shaped piece right here. Now, we're revolving this about the line x equals -2. Unfortunately, because it's such a skinny thing, it's hard to see, but the rectangles that we're going to draw are going to be thin rectangles in the y direction. So the height this time is going to be dy. Now, it's going to be a little tricky for me to do this, but I'll try. We want to draw this rectangle, its mirror image, way over here. Oh, wow. Okay, so we've revolved it, I've reflected it over the line x equals -2. I've reflected that rectangle, and now I want to imagine connecting these pieces by drawing my disc, or in this case it's going to be a washer. So the inside is going to be here, and the outside will be way out here. Okay, so I think it's really important to draw the mirror image of those rectangles as you do this. I think it really helps you set up the picture, especially if your cylinder drawing skills are a little bit suspect. Okay, this is the most challenging part of all of this. Okay, we want to know what the inner radius is. Okay, so here is the inner radius. We're going to start here at the axis. You always want to start at the axis of revolution, which in our case is x equals -2. And we're going to move out to this point here. So this is the inner radius. Now, I've only drawn it. I haven't really thought about the whole process. Well, let's think about this. We're moving left and right. If I'm moving left and right, x values are changing. Where do they start? Well, we start out here on the left at x equals -2. On the other hand, we end when we reach the left-hand endpoint of that rectangle. Well, where is the left-hand endpoint of that rectangle? The left-hand endpoint of that rectangle is on this particular curve. Okay, it's on the line. Now we have a slight problem. We're going to be integrating with respect to y. The function that I just drew, I knew as y equals 2x. If I'm integrating with respect to y, notice we went from x equals -2 this way. We want to know what x is equal to. We want to know what x is equal to. Well, I know that y is 2x, which means that x is equal to 2 or 1/2 y. Okay, so this x value here is x equals 1/2 y. That's not the radius, okay? We've got to be very careful here. The radius is that distance between these two values, between x equals -2 and x equals 1/2 y. Now pause for a moment. Let's pretend we're moving from x equals 12 to x equals 17. How far have we moved? And I'm sure it was pretty obvious that the answer is 5. How do we get that? We took the difference of the larger number minus the smaller number. The larger number here is on the right side. So in our case, our inner radius is the number on the right side, which is 1/2 y, minus x equals -2, or 1/2 y plus 2. Wow, this is getting messy. So my inner radius is 1/2 y plus 2. Okay, now I still have to draw on the picture. I want to know what the outer radius is. Well, the radius, remember, you start at the axis of revolution. So we started here, once again, at x equals -2. And we're going to stop when we get to the right-hand endpoint of that rectangle. And the right-hand endpoint of that rectangle was on the curve y equals x squared. Oh, darn it again. Y equals x squared. I need to know what x is. X is going to be the square root of y. Notice that we're in the first quadrant. In the first quadrant, the x values are positive, so that's why I chose the positive square root. That means my outer radius, and this is where we're getting messy, we're moving left and right. My outer radius is the right-hand endpoint of that rectangle. Well, that's the square root of y. We're going to subtract the left-hand endpoint, which once again is negative 2. So we end up with the square root of y plus 2. My outer radius is radical y plus 2. My inner radius is 1/2 y plus 2. And so now we're almost ready to go. We're going to be integrating with respect to y. Since I'm integrating with respect to y, yes, I have to draw one more thing on this picture. I need to know the y values in that region. Okay? Well, that region is here. I'm shading it. The lowest y value in that region is y equals 0. The highest y value in that region is way up top here, which is y equals 4. We're ready to set it up. Oh, are we really ready? Are you ever ready to set this up? So our volume is pi. We're going to do the integral from 0 to 4. And here's where we talk about the squaring of the radiuses. We could do outer radius squared times the thickness minus the inner radius squared times the thickness, both of which are multiplied by the thickness, which is dy. So we could factor that out. We'll have the outer radius squared minus the inner radius squared. So that's pi times the integral from 0 to 4 of the outer radius we decided was radical y plus 2 squared. The inner radius we decided was 1/2 y plus 2 squared dy. So what I'm going to do is I'm going to expand out each of these, and because the video is getting a little bit long, I will leave some time, but I'll write in the answers and pause after we're done here. And in the end, we end up with a nice 8 pi. Now, I do want to make a couple of comments about the arithmetic algebra that we get along here. It's really, 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 really helpful if you do some simplification. So from here to here, we expanded things, and then we distributed the negative through to each of these. The 4s we could cancel, 4 minus 4. The y minus 2y became negative y. So you want to take advantage of that whenever you can.